Welcome to Omni. Today, we explore the astonishing world of the praying mantis, a tiny creature possessing incredible three-dimensional vision. Do you believe that an insect could rival human depth perception? Prepare to be amazed by this extraordinary biological marvel of nature. In episode 14, we dive deep into the microscopic jungle to uncover the lethal secrets of this fascinating and deadly little assassin. Unlike most insects that merely detect fleeting motion, the praying mantis relies on an advanced stereoscopic visual system to secure its prey. This unique evolutionary advantage allows them to calculate exact distances with absolute precision, making them one of nature's most formidable ambush predators. Observe the complex structure of their head. Two massive compound eyes sit perfectly positioned on either side, granting a wide, overlapping field. This specific anatomical arrangement is the fundamental key to their remarkable three-dimensional sight, functioning very similarly to our own human eyes. When an unsuspecting target wanders into their domain, the mantis remains perfectly still, silently evaluating the exact trajectory of approaching meals. Its tiny brain instantly receives two slightly different images from each eye, processing the visual disparity to compute precise striking distances. This biological computation happens in a fraction of a second, ensuring the mantis strikes with deadly accuracy before prey can react. The rapid extension of its spiked forelegs is a masterclass in biomechanical engineering, executed flawlessly thanks to perfect depth perception algorithms. Without this incredible stereoscopic ability, the mantis would blindly grasp at empty air, wasting precious energy and ultimately facing certain starvation. To truly understand this marvel, we must look closer at the individual lenses that make up these fascinating alien compound eyes. Thousands of microscopic photoreceptors work together in perfect harmony, capturing tiny fragments of light to build a comprehensive visual mosaic instantly. Each individual ommatidium acts as an independent camera, feeding crucial environmental data directly into the central nervous system for rapid processing. The overlapping fields of view from both eyes create a binocular zone right in front of the insect's triangular-shaped face. Inside this critical zone, the mantis possesses unparalleled spatial awareness, allowing it to judge spatial relationships with absolute pinpoint accuracy. Scientists have spent decades studying this phenomenon, outfitting tiny insects with miniature colored glasses to test their three-dimensional visual capabilities. Through these clever experiments, researchers conclusively prove that mantises utilize binocular disparity, just like humans do when navigating complex environments. However, the insect brain achieves this monumental task using a mere fraction of the computational power found in mammalian neural networks. This extreme biological efficiency represents a masterpiece of natural optimization, stripping away unnecessary details to focus solely on moving targets. While we perceive a rich tapestry of static depth, the mantis specifically calculates the distance of objects that are actively moving. If a delicious fly remains completely motionless, it might become invisible to the specialized depth perception algorithms of the mantis. But the moment that fly twitches a wing, the insect's neural circuitry locks onto the target with terrifying and lethal precision. This motion-based stereoscopic vision is entirely unique in the animal kingdom, showcasing an alternative evolutionary pathway to spatial awareness. Imagine processing complex geometric calculations using a tiny brain smaller than a pinhead, yet achieving results that rival modern digital supercomputers. Nature has elegantly solved the mathematical problem that human engineers have struggled with since the dawn of early robotics and automation. By studying this miniature predator, we unlock profound secrets about visual processing that directly influence our most advanced technological innovations today. Every time you take a stunning portrait photo with your modern smartphone, you are utilizing principles perfected by the praying mantis. The dual camera systems on flagship devices mimic the insect's compound eyes, capturing two distinct perspectives to generate artificial depth maps. Software algorithms analyze the slight differences between these two lenses, calculating distance to blur the background and highlight the main subject. This artificial bokeh effect relies entirely on the exact same stereoscopic geometry that guides the deadly strike of our tiny assassin. Furthermore, advanced smartphones and autonomous vehicles now incorporate sophisticated LiDAR scanners to map their surroundings in glorious three-dimensional high resolution. LiDAR emits rapid pulses of invisible laser light, measuring the exact time it takes for reflections to bounce back to sensors. While LiDAR uses active light projection, the Mantis relies on passive light reception. Yet both achieve remarkably similar spatial mapping results. The sheer computing power required to run modern LiDAR systems is absolutely massive compared to the humble neural network of insects. Our silicon processors consume significant electrical energy to calculate depth, generating substantial heat and requiring large batteries for sustained daily operation. In stark contrast, the praying mantis performs these complex calculations using less energy than a single microscopic drop of morning dew. This incredible disparity in energy consumption has captured the intense attention of ambitious robotics engineers and visionary computer scientists globally. If we can successfully replicate the elegant neural algorithms of this insect, the future of miniaturized robotics will change forever overnight. Imagine deploying swarms of autonomous microdrones, each no larger than a bumblebee, navigating flawlessly through dense and hazardous collapsed buildings. These tiny mechanical marvels could easily slip through narrow crevices, searching for trapped survivors without ever colliding with dangerous structural debris. Currently, shrinking conventional sensors and heavy batteries to such microscopic scales remains an insurmountable challenge for modern hardware engineering and design. But by adopting the streamlined visual processing techniques of the Mantis, drones could process crucial depth information using minimal computing power. This biomimetic approach allows machines to ignore irrelevant static background details, focusing strictly on dynamic obstacles that pose immediate collision threats. As a result, the onboard processors can be drastically reduced in size, shedding unnecessary weight and significantly extending operational flight times. The natural world continuously proves to be our greatest teacher, offering elegant solutions to our most complex modern technological engineering hurdles. Look closely at a praying mantis, perched silently on a vibrant green leaf, waiting patiently for the perfect moment to strike. It is not merely a simple bug, but a highly sophisticated biological machine, perfected by millions of years of ruthless evolution. Its calculating gaze processes the environment in a way that fundamentally challenges our traditional understanding of vision and spatial awareness mechanics. While mammals rely on complex visual cortexes to render detailed three-dimensional worlds, this insect takes a brilliantly minimalist computational shortcut. It extracts only the most essential geometric data required for survival, discarding everything else to maintain lightning-fast physical reaction times. This ruthless efficiency is precisely why the mantis boasts one of the highest successful hunting strike rates in the animal kingdom. When those powerful spiked forelegs shoot forward, they are guided by an infallible biological targeting system that rarely misses its mark. We can observe similar evolutionary adaptations in other apex predators, but none package such profound capability into such a microscopic frame. The more we analyze the intricate neural pathways of these creatures, the more we realize the limitations of our silicon chips. True artificial intelligence and machine vision will likely require a fundamental paradigm shift, moving away from brute force data processing methods. Instead, we must embrace the elegant, task-specific algorithms demonstrated by the praying mantis to achieve true mobile robotic autonomy. Researchers are already designing novel neuromorphic microchips that physically mimic the structural architecture of insect brains to handle visual data efficiently. These experimental chips process information through artificial synapses, drastically reducing power consumption, while dramatically accelerating real-time spatial recognition and analysis. Imagine a future where your smart glasses can instantly map your environment without draining their tiny onboard batteries within mere minutes. This transformative leap in wearable technology will be made possible by unlocking the ancient biological secrets hidden within insect optical systems. The humble bug hiding in your garden holds the master key to unlocking the next massive revolution in global consumer electronics. It is a humbling realization that despite all our massive technological advancements, nature remains the ultimate, undisputed master of efficient engineering. Every intricate detail of the mantis anatomy serves a specific, optimized purpose, honed through countless generations of fierce environmental survival challenges. Its triangular head can pivot a full 180 degrees, scanning the surroundings with unparalleled and terrifying predatory focus. This incredible mobility, combined with stereoscopic vision, creates a biological radar system that leaves absolutely no blind spots for potential prey. When we observe this creature through the lens of modern science, it transforms from a simple bug into an engineering marvel. The integration of sensory input and mechanical output happens so seamlessly that it borders on what we might consider pure magic. Yet, it is not magic, but rather the profound result of relentless evolutionary refinement, operating at a microscopic cellular level daily. As we continue to push the boundaries of what machines can do, biomimicry becomes an increasingly crucial field of scientific study. We are no longer just building tools. We are attempting to recreate the very essence of biological life in synthetic forms. The praying mantis serves as a perfect blueprint for this ambitious endeavor, offering a roadmap to smarter, faster, and lighter machines. Consider the implications for space exploration, where every single gram of weight and microwatt of power is absolutely critical for success. Autonomous rovers equipped with insect-inspired optical sensors could navigate treacherous alien terrain with unprecedented agility and remarkable energy conservation capabilities. These robust systems would be highly resistant to the intense radiation that typically destroys complex, traditional computer processors in deep space. Back here on Earth, agricultural drones utilizing these same principles could dart through dense crops, monitoring plant health with surgical precision. They could identify and eliminate harmful pests individually, drastically reducing the need for widespread toxic chemical pesticides in modern global farming. The potential applications are virtually limitless, spanning across medicine, agriculture, search and rescue, and advanced planetary exploration in the near future. All of these grand technological visions trace their origins back to the unique stereoscopic vision of a tiny, predatory green insect. It reminds us that true innovation often requires us to look closely at the seemingly insignificant creatures sharing our vibrant planet. The microscopic realm is filled with countless untold secrets, waiting patiently for curious human minds to discover and harness their potential. Omni is dedicated to uncovering these hidden natural wonders, bridging the fascinating gap between wild biology and cutting-edge technology. We believe that the next great scientific breakthrough will not come from a laboratory, but from observing the wild, natural world. As we marvel at the praying mantis today, we must ask ourselves, what other incredible biological mechanisms remain completely undiscovered worldwide? Could the complex flight patterns of a dragonfly inspire the next generation of hyper-agile supersonic passenger jets in the future? Might the structural integrity of a microscopic beetle shell lead to revolutionary new lightweight armor materials for our brave first responders? The intricate web of life on Earth is a vast, open-source library of brilliant engineering solutions waiting to be read. By studying these tiny assassins, we gain a profound appreciation for the immense complexity woven into every single living terrestrial organism. Their existence challenges our technological arrogance, proving that nature solved complex spatial computing problems long before humanity even existed on Earth. This realization should inspire a deep sense of environmental stewardship, urging us to protect these invaluable biological databases from mass extinction. Every species lost is a destroyed blueprint, a permanently erased solution to a problem we might desperately face in our future. The praying mantis, with its remarkable three-dimensional vision, stands as a powerful testament to the sheer brilliance of evolutionary design. It bridges the gap between raw biology and advanced physics, seamlessly merging optics, neuroscience, and deadly biomechanics into one perfect form. As we conclude our deep dive into this microscopic world, take a moment to reflect on the wonders surrounding us daily. The next time you see a mantis, you will not just see an insect, but a living, breathing, technological miracle unfolding. You will recognize the same sophisticated visual processing power that currently resides inside your expensive smartphone, resting quietly in your pocket. Omni will continue tracking these incredible advancements, bringing you the most fascinating intersections of nature and modern human technological progress. We are constantly amazed by the intricate details of the natural world and how they shape our rapidly evolving digital future. What are your thoughts on the astonishing three-dimensional vision of the praying mantis and its impact on future robotics engineering? Do you think we will soon see swarms of micro-drones navigating our cities using these exact same biological visual principles? Please share your unique perspectives and insightful ideas about this fascinating topic in the comments section located directly down below today. If you enjoyed this journey into the microscopic world, Make sure to like this video and subscribe for more amazing content. We have many more incredible stories about the brilliant designs of nature planned for our upcoming episodes in the near future. Thank you so much for watching this episode, and as always, keep your curiosity alive with Omni Eyes. See you soon!